example. You guys, some of you may or may not have seen that TV episode Breaking Bad. Okay, there's one scene where they're cooking meth. Okay, so it's basically a chemistry high school teacher who cooks meth because he needs the money. Okay, that's not your typical chemist. There's some garage chemists that might try and do that, but that's not how we we're generally not on the dark side. Although we have the ability to be in the dark side by figuring out, because the chemical reaction is not that difficult. Okay, it's getting the ingredients, but that's all I'm going to say about that. But anyway, Breaking Bad's about this high school chemistry teacher that hooks up with this guy, and now they're cooking meth and making a lot of money. So they need to go to a place where the chemical fallout, the residue, can't be detected. So they go out to the desert, buys a mobile home, goes out to the desert, and they start cooking this meth. And because he's a chemist, it's one of the most purest meth that is in the market. Okay, at least that's what's happening. Anyway, they're out there cooking meth and everything, and then their battery dies on their Winnebago, and they're like probably hundreds of miles away from civilization. They gotta get somehow they gotta get their Winnebago going. So he uses his chemistry knowledge again to make a battery. And what does he do? He uses copper and zinc. Use copper and zinc in this particular case, and this is basically it in terms of that. Or maybe he uses iron and zinc. Anyway, you can use different materials, and if you plan it just right, you can get an electron to flow through an external circuit as one species gets oxidized, the other species gets reduced, and then you can do work for you. Okay, so if your ambitions is to be a chemist, then you too will have knowledge about making batteries, or you don't have to be a chemist to do that. You can actually make a battery from potatoes or lemons. And you guys probably have seen that in these science project in grade school.
We need to begin by putting our nails into our potato. So you need to put one zinc nail in and one copper nail in. Now, to check that it's generating power, I'm going to put my voltmeter on it. There you can see it's generating power. Now, if we wanted to generate more power, we could add another potato. So, once again, we put zinc nail in and a copper nail in. Now, using our wire, my wire has got crocodile clips, but you can use any wire and just wrap the ends around the nails. Now, what's very important is you need to connect one end to a copper nail, which then goes to a zinc nail. Now, we'll see that it's generating more power.
Anyway, let's take a look at this reaction. This is your typical reaction in terms of generating electricity. We have zinc and copper. Why? Because one species here is really good in getting rid of its electrons. Another species is really good in accepting electrons. So we have a species that is really good in being oxidized. We have another species here that's really good in being reduced. So if you take a zinc and put it into a solution, and that solution has copper ions in it, then what will happen over time is that the blue color here is actually an indicator of copper ions. Copper ions, and you guys may have seen this in maybe previous examples. Copper ions is blue in water. Okay, but when you reduce that concentration, then the blue lightens up, and then you get the copper solid plating out, and the copper solid looks brown or looks like it's rust, but it's really a copper solution. So that reaction will happen because what's going on is that the copper is getting reduced, going from copper +2 to copper 0, and the zinc is getting oxidized. It's going from zinc 0 to zinc +2. So what you will see here is that the metal is going to corrode and the copper is going to build up. So that's basically what's going on at the molecular level. Okay. Now, if we just put two solutions together, okay, where we have zinc and zinc sulfate here, maybe we have zinc sulfate here, and we get copper and copper sulfate here, then we can get that reaction to go, but then it'll stop. And the reason why it stops is because the electrons are going to get transferred here, and then you get a charge buildup. Whenever you have a charge buildup, that's going to be like a barrier to stop the electron from flowing. You gotta complete the circuit. It's the same reason why you need to switch the switch on your home to turn on a light, because when it's off, the circuit is open and the electrons aren't free to move around. As soon as you close it, then the electrons can move about, turn on your light bulb, and then go back out into the ground. Okay, but that's basically how electricity operates in your home. You turn it off, you open up the circuit, the electrons can't flow anymore. You close it, you close the circuit, the electrons can flow and it can do work. So here you have an open circuit, the electrons can't flow, your reaction is not going to go. What you need to do is you need to complete the circuit. And the way you complete the circuit is you basically would put what we call a salt bridge for the two, so that any electron buildup on this side is going to be counteracted by any ions, positive ions is going to neutralize it, and then the negative ions will go over here, so that any positive deficit on this side or positive buildup on that side is going to be neutralized by negative ions. So we need a salt bridge to complete the circuit, in other words. In a battery, we have something called an anode and a cathode. And what eventually will happen is that electrons will be generated from the anode. That's where electrons originate from. And then they'll go to the cathode. Okay, but in the process of doing that, it's going to go through an external wire, and then it can generate, it can do work for us, like start our engine. So that's what we have right here. Okay, that's what we have right here. This is a typical battery. We have our zinc, and we have our copper. The place that undergoes oxidation, remember, zinc is going from 0 to +2. That's the oxidation reaction. So the place that undergoes oxidation is always your anode. Oxidation. Now this is for a voltaic cell. This is for a voltaic cell, is the anode. That's where the electrons originate. Okay, that's where the electron originate. And the anode's negative. Anode, think of anions. Anode, anions. Anions are negative, right? So that's where the electrons originate, and then they can go through this electric external circuit right here. Can go through this external circuit right here. Okay, it can do some work, or you can read it through a voltmeter, and then it heads to the copper, and the copper accepts it, and the copper gets oxidized. It goes from copper +2 to copper 0. So what's going to happen here is that the copper is going to start plating out over here. Then there's ions here. This is your salt bridge right here. And because there's a buildup of negative charge on this side, it's got to be counterbalanced by the sodium migrating to that side. Okay, the electrons build up, it's got to be counteracted by positive cations flowing to that side. That means that the negative anions are going to be flowing on to the left side to counteract the fact that this side, because it's losing electrons, is going to start building up its positive charge reservoir. If it's increasing its positive charge, then the negative ion is going to neutralize that. So that's the flow of the salt bridge. It's got to have ions in it, and those ions got to be made from strong electrolytes. They need to be able to break apart. And then one side is going to get a migration of positive ions, the other side is going to get a migration of negative ions, so that everything is complete and there is no charge buildup. Okay, again, the side that undergoes oxidation is called the anode. The side that undergoes reduction is called the cathode. This is where reduction occurs. Remember, reduction, gain electron reduction, GER, lose electrons oxidation, LEO. So when you gain electrons, this is where electrons are being gained, right there. You got your reduction. That's your cathode. Remember, cations are positive charge. Okay. The cathode's also labeled red. The anodes are black. If you look at your battery, okay, if you had problems with your battery like I had a couple of weeks ago, okay, one is your car battery, that is. One is negative, one is positive. If you're going to jump your battery because your battery is dead, you hook up your cathode for your cathode first, your positive, and then you hook up your anode last, and then you don't really touch it to the negative terminal. You connect it to the metal of your car. That way, if there's spark, there's no spark in the vicinity of the battery, because the battery sometimes will generate hydrogen gas, and if it generates hydrogen gas and there's a spark there, it could explode. I've never seen a battery explode, but that's what they tell you. You connect to one car, you put your positive and negative. To the car that needs to be jumped, you put your positive terminal first, that's your cathode, and then you take your negative terminal and you connect it to one of the metals on your car, and then you can start your car. Okay. Then they tell you, this is on the side, but they tell you that the first car that's supplying the battery shouldn't be running. Why? Because they say that now with all the computer parts to your car, it might send a back charge to that other car and then ruin the computer. It's never happened to me. I've always run both cars, but just so you know, there's a lot of practicality to batteries. Anyway, this is a battery right here. This is what your AAA battery, your AA battery, or car battery will have. It's basically transferring electrons from one to the other through a chemical reaction. Okay, so this is a summary of what I just talked to you guys about. Anodes, black, negative electrodes, generates electrons, oxidation occurs. This is your cathode, red, positive terminal, accepts electrons, reduction occurs. Here it is again. In this particular case, we have this particular setup. This salt bridge now is here, and it's just basically what we have is just a semi-permeable membrane so that the ions can migrate to both sides. The anode is always where the oxidation occurs. And of course, if you have an oxidation, that's where the electrons come from. Why? Because you lose electrons, oxidation. The electrons will be originating from the anode, and then it will travel through an external circuit, external wire, and then head over to the cathode. And when the electrons reach the cathode, the electrons will be available to reduce whatever chemical species is there. And remember that it would be LEO GER. GER would be gain electrons reduction. So when the electrons hit the cathode, that's your reduction process. And the electron can now take a species and add to that species, and then the charge would get lowered. And that's why we call it a reduction, because the charge is lowered even though it's gaining an electron. Okay, so please keep that in mind. Like I said, electrochemistry can be confusing and it seems like it's backwards. Why? Because electrons are negatively charged. So when you give an electron away, you're giving a negative charge, and then that species that accepts the electron will get more negative. So we call it a reduction. Okay, so let's go ahead and continue here and talk to you guys about, I already talked to you guys about this, where the anodes, where oxidation occurs. And the example that I'm giving here is the oxidation of zinc and the reduction of copper. Okay. And if we carry out this reaction under standard conditions. Yes, there is a standard conditions for electrochemistry as well. What are standard conditions? Well, it will be the same as thermodynamics, where we have 298 Kelvin, 1 atmosphere pressure, but the concentrations are 1 molar for solutions. Okay, so under standard conditions, we will get a potential of 1.10 volts. What does the potential mean? It means that you can think of electricity, for those of you who've taken physics, in terms of water flowing in a pipe. Okay, when you have pressure, that's like the voltage. When you have volume, that's like the amperes. So the number of electrons passing through a certain point will determine the amount of electrons that are passing through. So the voltage here has to do with how much electrons are passing through a certain point. So what I want to show you now is how that 1.10 volt comes about. Okay, remember that zinc is where oxidation occurs. Copper is where reduction occurs. Of course, it's not copper 0 that gets reduced, because you can't go from copper 0 to copper minus. It's going to be the cation that gets reduced, copper +2. So you got to have copper +2 in that mixture where the electrons are coming in. So what we have is this right here. Now, where does this come from? Okay, well, the electrochemical potential for the oxidation of zinc is 0.76. The electrochemical potential for the reduction of copper is 0.34. So when you add those two, you're going to get 1.10 volts. And remember, one has to be an oxidation, the other is a reduction. Once you change one, once you reverse the reaction, then that sign changes, okay? Because it's related to thermodynamics. If in one direction it's giving off electrons, in the other direction it's going to be accepting electrons. Now, where did those numbers come in? So let me just break away here, and let me take you to my webpage, because you guys will be needing to use this, okay? So if you go to my webpage and then you go, of course, to the fog links, this is where I accumulate a lot of resource for you guys. Go to the information and equation, and then go to Chem201, okay, right here. And in there, you will see, for those of you in lab, this is actually your appendix in your lab manual. Since I wrote the lab manual, I was able to get a lot of resources and try and make sure that I consolidate it so that you guys don't have to like hunt everywhere to get the information you need for the experiment. But anyway, if we scroll down here, okay, what you will see, and again, when you guys are using the lab, when you're doing calculations, try to use this information, because if you use another information, then the numbers will vary. And when I'm setting up the key, I use these values. So here's the periodic table, here are the Ka, here's the electrochemical potential. Now it's going to be sideways. And it says it's been updated 509. Actually, I need to update that because I've updated this past couple of years. So of course, it's difficult for you guys to read this sideways. So let me just, I took a screenshot. And here is the electrochemical potential. And let me show you how to read this thing, okay? Because it's important that you know how to read this thing so that you understand the ways the electrochemical potential for a voltaic cell is calculated. First of all, zinc to zinc +2 is an oxidation. If you look at this table, it says standard reduction potential in aqueous. It's an aqueous solution at 25 degrees. So basically says standard state, okay? And what you need to do is these two columns right here are the conditions under acidic medium. You will see that in a lot of these things, if you need hydrogen, it's H+. Okay, if you need hydrogen, it's H+. Let me blow this up. I hope you can see that. It's H+. Whereas this right here, it's under basic medium. So depending on the conditions in which you're trying to calculate the electrochemical potential, you either need to look at under acidic medium or basic medium. Now, if it doesn't say anything, just assume it's acidic medium. Now, what we're going to do is look for the oxidation reaction for zinc. Now, if we look over here, what you want to do is just scroll through and look for zinc. And remember that sometimes the oxidation or reduction process involves multiple electrons. Some reactions, some metals, for example, will involve one, some will involve two, some will involve three. So you got to find the correct half reaction that corresponds to the number of electrons exchanged. That's very critical, okay? Because if you pick the wrong one, you're going to be using the wrong number for your calculation. Anyway, and then, of course, remember the symbol of your element. Zinc is Zn, not Zr. Zr is zirconium. Zinc is Zn. Here it is right here. Okay, here it is right here. Now, if you look at that reaction right there, you will see that that's a reduction reaction. It's a reduction reaction. Why? Because this table tells you this is a reduction. Let me just show you. This is a standard reduction potential. So all of these reactions are reduction potentials. What does that mean? It means you're gaining electrons, gain electrons reduction. So you gain electrons, you put the electrons on the left side, the reactant side, and then you're going from a higher charge to a lower charge, zinc plus 2 to zinc. But we want a reaction in which we have an oxidation. So what does that mean? Well, we need to take this value right here and change the sign, because the problem we're solving is not a reduction, it's an oxidation. So the negative of negative 0.763, and I'm rounding up to the hundredth of a place, is 0.76, positive 0.76. And that's the reaction that we're interested in this voltaic cell. It's the oxidation of zinc. So rather than write negative 0.763, I write 0.76, because that's the reaction that's taking place. It's the oxidation reaction. Now I look for the reduction of copper. Now that I should find in this table. Why? Because this is a standard reduction potential. So I'm just going to, again, scroll through here and look for copper. And here it is right here. You might think that, okay, this is my copper, but notice, please notice, this is copper 2 going to copper plus 1. That's not the reaction you want. It's not the reaction you want, okay? Yes, you're starting out with copper 2, but the end product is copper 1. You don't use copper. It's not going to copper 1. It's going to copper 0. It's going to copper 0. So what you need to do is you need to scroll some more and find that potential that leads to copper plus 2 to copper 0. And here it is at the very bottom, right here. Okay. And that's a reduction potential. And so you would write 0.337 or 0.34. Okay, try and use the whole significant figures when you're doing this. I think I just got this from another book, and so I just put 34, and it's positive 0.34 because that's the way it's found in this table. So we have an oxidation, we have a reduction, we just add the two and we get the potential. Remember, you got to have an oxidation and a reduction. Now, some sources like your book will give you another formula. It's the same concept, and that formula is this right here. Okay, that formula is this right here. It tells you the electrochemical of the cell. This is the electrochemical of the cell is equal to the reduction potential. Where does reduction occur? That's where the electrons are heading. Okay, that would be the copper, minus, this is important, this is really important, okay? I want to highlight that. Minus the reduction potential. This is the reduction potential at the anode. So the way you use this equation, it looks different from what I just discussed, but it gets you to the same result. The way you use this equation is you look at the copper potential, that's point, that would be in this particular case, 0.34 volts positive. And you look at the reduction potential for zinc. Yes, zinc is being oxidized, but you want to find it as a reduction potential in this table. And that value was over here. We said that it was, again, don't use zirconium. It's not zinc. Zinc, I believe, was over here at 0.7. Yeah, right here. Okay, negative 0.763. So the negative here, okay, switches it for you. So when you take 0.34 and you take a minus 0.76, guess what? That becomes 1.10 volts. So that's the way this particular equation works. Okay, that's the way this particular equation works. It's the way it's presented in your textbook when they want to talk about the calculation of the reduction potential for redox reaction. They just take the cathode minus the anode, the reduction potential, minus the reduction potential at the anode, as is from the table. And when they do the math, it's the same as doing it this way. I like doing it this way because you can actually see which reaction is being oxidized, which is the oxidation reaction, and which reaction is being reduced. But please remember that when you do it this way, you've got to manually change the sign from the table. You've got to manually change the sign from the table because the table is a reduction potential. When you're writing it as an oxidation, it becomes the negative of that. When you use this equation, you just accept the values as found in the table. Okay, so please either stick with one convention or the other. Don't confuse the two. Don't confuse the two, because what some of you will do come next week is you're just going to put a negative here and then add it. You're going to put a negative right here and add it, and then you're going to be completely off. Okay, so please make sure you understand how these two techniques of calculating the reduction, the electrochemical potential of the cell. When we say electrochemical potential of the cell, it means both the oxidation reduction of the electrochemical potential of the cell is calculated. You can look at each half reaction, find the electrochemical potential for each half reaction, adjust it, or use that formula that's provided, and just use the electrochemical potential as found in this table. And remember, this table is going to be found in, you guys should make sure that you download this. If you're going to be using resource, I'll also have it available as a link when I give you your quiz, but it's always going to be found right here. It's also in your lab manual for those of you who have are taking lab. It's the information and equation. And these are the resources that like if you were taking the exam on campus, I would give you this equation page, because as long as you know the concepts and know how to use the equations, that's the important thing for me. Okay, you don't have to really memorize things because you will always have resource to look up, but you got to know how to use the equations when you're presented the equations or the data. So that's why I have no problems for you guys using this particular resource when you need information. Okay, so scroll down. Here's the standard reduction potential. It's also in your lab manual. So let me move on. Okay, let me move on from here. So there is a, again, the evaluation of E0 is based on the two half reactions coming together. Now, theoretically, you can just calculate one of the half reactions, but in reality, you're going to need both. If one reaction needs to give up an electron, there's got to be some other reaction that picks up the electron. Okay, you can't in in the real world, just have half a reaction, but you can have half a reaction in the theoretical world. Okay, you can't calculate the E potential for a half reaction. That's possible. So again, this is just a summary of what I talked to you guys about, this equation right here. The cathode, the reduction potential, minus the anode, the reduction potential at the anode. Okay, so here's another voltaic cell. This one couples zinc, not with copper, but with hydrogen. Hydrogen can either do this or this. That's your reaction for the oxidation of hydrogen gas to hydrogen ions, or the reduction of hydrogen ions to hydrogen gas. So that's the reaction that you would need. But of course, hydrogen is not a metal. So you can't put like a metal hydrogen electrode in there. What you need to do is you need to figure out how to get this reaction going, but through some sort of what we call a sacrificial electrode that will facilitate electron transfer. And so in this particular setup, what we have is we have hydrogen gas being bubbled into a solution with hydrogen ions. And the concentration of those hydrogen ions is 1 molar. So it's a 1 molar hydrogen ion solution, like 1 molar hydrochloric acid, in which we bubble 1 atmosphere of hydrogen gas. Again, we are at standard state, okay? So, but of course, we can't use hydrogen as an electrode. So what do? We use something called an inert electrode. And the inert electrode is simply a substance, a material in which it itself will not undergo oxidation and reduction. Okay, otherwise the reaction is not going to be happening with the hydrogen. It's simply there to facilitate the electrons and pushing it into the cathode cell. So once it transfers the electron to the cathode cell, then the hydrogen ions will get reduced. It'll go from H plus to H0. Okay, the electron source is still zinc because that's what we have in the anode. Okay, so the half reaction here would be zinc undergoing oxidation and hydrogen undergoing reduction. And you can't put hydrogen plus going to hydrogen atom. The way nature gives us hydrogen is H2. So don't write H plus going to H. That's not possible. It's H plus going to H2. You guys know that because hydrogen is a diatomic chemical. So the balance equation is this right here. Okay, and then you can add the 2 half reactions and get the net reaction. But again, the E0 for this is positive 0.76 volts for the oxidation of zinc. The reduction of zinc, again, is negative 0.76, but I'm writing it here as an oxidation. And what is the reduction potential of hydrogen? Well, the reduction potential of hydrogen, so if you look, you'll see it right here, right in the middle of this table. And that's because that is our reference electrode. What do we mean by reference? If you remember thermodynamics, right? We talked about scales. We said that, okay, in order to calculate the enthalpy of a reaction, we can compare the enthalpy of one reaction to another and then calculate the net enthalpy for the net reaction. And we said that we got to have a reference so that we have a 0 point. It's kind of like if you try and weigh a baby, okay, a child. Suppose you have a 1 month old and you're trying to get the mass. Try and put your child on a scale. They're going to squirm and move around. You're not going to get a constant mass. So what do? Well, it's easy. Parents know this all the time. What you do is you hold your child or the baby and you step on the scale. You get the total mass. And then you hand off the child to your significant other or to a caretaker, and then you weigh yourself. And then the difference is the mass of the child. That's the way reference scale works. We have a reference point in which we can say that that's 0, and then we can calculate all others relative to that. Now, entropy doesn't have a reference scale. It has an absolute. At 0 Kelvin, pure crystalline solid, we have 0 entropy. But most others, we have a reference scale. That's no different from electrochemistry. What we do is we assign one reaction at standard state a 0 potential. That doesn't mean that it won't occur because it's 0. Again, this is only half a reaction. It depends on what it's coupled to. Okay, it depends on what it's coupled to. And then the two combined will give you the electrochemical potential. So the hydrogen electrode is simply the 0 point that we've assigned. And so if we couple that to zinc, now that's 0 volts right here. You see that? See how it's 0? If we couple that to zinc and we say that's 0, whether it's an oxidation or reduction, it's 0 volts. Okay. If you take the negative of 0, you still get 0. Okay, so the potential here when you couple the zinc oxidation with hydrogen is 0.76, and that's basically what you will see in your voltmeter. That's what you would see. Of course, you need to calibrate your voltmeter, and this is one way of doing it. You get a certain voltage and say, okay, under standard state, that amount of voltage should equal 0.76. So that's one of the ways you can do that. And then you can measure the rest of the potential relative to the hydrogen. So that's it. If you want to do the equation that we talked about, then E cell equals the reduction minus the oxidation. But that's the reduction. That would be 0 minus a minus 0.76. And that's positive 0.76, the same as that. Okay, same as that. You get to the same place whether you're looking at each half reaction, figuring out the E0 for that, or doing the equation that's presented to you in the book. Okay, it's the same idea, So again, I wanted to introduce this half reaction from hydrogen because now you can see why some of these have positive potential right here, and some of these have negative potential. It's all relative to the hydrogen standard reduction potential. It's the 0 point. So if you try to couple any of the reactions below hydrogen to hydrogen, you would actually not get electron flowing. The electron would flow the opposite direction. Okay, these guys would not be reduction. These guys would be oxidation, because if you take the negative of this and couple it with 0, then you get a net positive. Only net positive electrochemical potential are spontaneous. Okay, only positive electrochemical potential are spontaneous. That means the electrons are going to flow. If you got a negative, then the opposite is going to happen. So here you get a glimpse of how electrochemical potential is related to free energy. Remember, in free energy, we said if it's a negative delta G, it's spontaneous. If it's positive delta G, it's spontaneous in the opposite direction. Well, later on, we're going to see an equation that relates delta G to E0, and you will see that there's a negative sign in there because a negative E0 is not spontaneous. A positive E0 is spontaneous. But we'll take a look at that when we get to that in the section. So this right here is the Voltaic cell for the reaction in which the zinc undergoes oxidized and it's coupled with the hydrogen. Okay, it's coupled with the hydrogen. And here's the setup. This is a movie. You could, if you go to, I think the Google Drive, you can get the PowerPoint directly, and it'll show you the movie. Anyway, the movie just kind of illustrates, tells you what I already have talked about. So let me go ahead and switch gears and explain to you or tell you about the line notation. Why do we have a line notation? Because it's too tedious to always draw the two halves, the two cells, show the connections of the wire, show the salt bridge, and then write the reaction. You should be able to just write a chemical reaction and be able to translate that chemical reaction to the cells, the two half cells in a voltaic cell. So here's the standard convention by which you do that. It's called the line notation. First of all, you always write the anode to the left, because generally when you write the voltaic cell diagram, that's what I've showed you so far. When you have a voltaic cell diagram, the left part is where the oxidation occurs. That's the anode. The right part is where reduction occurs. That's the cathode. So when you write this line notation, the left part of that equation is going to be the oxidation, the anode. The right part of that equation will be the reduction, the cathode. Okay, so you always write the anode followed by the cathode, the oxidation followed by the reduction. You put a line, a vertical line, when there's a phase boundary. What is a phase boundary? When you go from a gas to a liquid, when you go from a gas to an aqueous, when you go from aqueous to a solid, when you go from aqueous to a liquid. Whenever there's a phase, and what are the different phases? The different phases are solid, liquid, gas, and aqueous. Okay. Whenever there's a phase boundary, you put a line. Okay. And you put a double line for a liquid junction. What exactly is a liquid junction? It's where you would put the salt bridge. Okay, where the two cells are separated, where one reaction takes place and another reaction takes place, where the oxidation takes place and the reduction takes place. It's going to break up the reaction that you write into the oxidation reduction. Okay, it's what separates the oxidation reaction and the reduction reaction. That's the double line. And then you can put in the concentrations. And generally, if it's standard state, you don't need to do that. You just put E0 because it's assumed it's going to be 1 molar. But if it's not standard state, you need to put in the concentrations in there so that when they calculate the electrochemical potential under non-standard state conditions, they know what concentrations to use. Okay. So we will take a look at this. This is the half reaction that we saw in the previous slide, and we're going to write the line notation for that. Okay. So here it is. We have zinc right here, and the reaction is zinc going to zinc plus 2. Now you can write the ions in here. Okay, you can write the ions. You could say zinc sulfate if that's what the salt bridge is made out of. This right here could be hydrogen sulfate or sodium sulfate or whatever the counter ions is. Or you can just simply make that zinc plus 2. Okay, you can just make that zinc plus 2. It tells you what the oxidation of the products are when the metal gets oxidized. Okay, if it says zinc sulfate, you should already know that the zinc in zinc sulfate is plus 2 because sulfate's negative 2. So that's the oxidation reaction. It's zinc 0 going to zinc plus 2. Notice there is a line right here. Notice that there is, erase this, that this is the oxidation process. This is the oxidation reaction. So there's a zinc going to zinc plus 2, 1 molar. Like I said, you don't need to put that 1 molar in if you're assuming it's standard conditions. It's assumed, but it doesn't hurt. It doesn't hurt. You can certainly put aqueous in there. I'm just overloading you with information. If you got zinc sulfate, you got a electrolysis process, it's going to be assumed that your solvent is water. Okay. We have separated by a salt bridge right there. And then we got the reduction reaction. And here we write the reduction reaction as reactant going to product. So you don't want to write this copper 0 going to copper plus 2, because that's not how the copper gets reduced. It's a copper plus 2 or copper sulfate going to copper 0. Okay, and so that's what we see right here. That's what we see right here. That vertical line needs to be moved here because my formatting got messed up a bit. But you can see that it's basically how the reaction progress in this voltaic cell. It's the copper plus 2 going to copper 0. And then, of course, we have a vertical line saying that the aqueous is separated from the solid. And when you see these at the end as solid, they also represent the electrode. The elemental form of the species that's undergoing oxidation or reduction is also serving as the electrode. Okay, so that's the copper reaction. That's the copper reaction. It's not quite the hydrogen reaction that I showed you, but let me show you that shortly here. So that's the reaction that we saw, not the previous one, but the previous one that I talked to you guys about. Let's take a look at this one right here. So we've already looked at that. Let's take a look at that one right there. Remember, it's the oxidation of zinc coupled to hydrogen. So hydrogen itself is not going to be an electrode. We got something called a inert electrode. So you got to put that in the line notation. This part's still the same as the previous. The zinc is getting oxidized. It's 1 molar zinc plus 2, or you can put zinc chloride, ZnCl2, or zinc sulfate, depending on the salt bridge that you have. And then here we have the reduction of hydrogen, H plus going to H2. Now, it doesn't need to be balanced, okay? You don't need to put 2 right here because that's not the point of the line notation. The line notation just tells you what the chemical species are that's undergoing oxidation reduction. And then when you break it up to the half reaction and you need the net reaction, then you would balance it. But you don't need to balance it in the line notation. When you get information from that and do a calculation, like what is the electrochemical potential for this particular cell, then you want to get both half reaction and probably balance it. Why do you want to balance it? Because you need to know the number of electrons exchanged. Why do you need to know the number of electrons exchanged? That's an important part of converting electrochemical potential to free energy. Okay, so they will require you to balance the equation eventually. But look over here. We got a line right here to separate the aqueous to the gas. And then we have another line separating the gas to the solid. And the solid is platinum inert electrode. Now, platinum's not going to be involved in the reaction. It's just there to shuttle the electrons for the hydrogen to get reduced. So that would be the line notation. If I gave you this line notation right here, you should be able to diagram this cell right here. Okay, you should be able to give me an illustration of what the voltaic cell would look like if I gave you the line notation. If I give you the cell diagram, you should be able to give me the line notation. Okay, you should be able to go both ways. So here are more examples of the line notation. Here you can see it's zinc and hydrogen. That's what we already covered. Here it's going to be iodine. That's at the anode with permanganate, MnO4 minus. So the iodine's getting oxidized. I minus going to I2 because that's the oxidation reaction. Negative going to a higher charge. Okay, the permanganate MnO4 minus going to Mn plus 2. Now, you need to make sure you understand why that's the reduction reaction. Yeah, it's going from minus for MnO4 to positive for Mn plus 2, but that's just the charge of the species. What is being reduced in that reaction is the manganese. Okay, it's the manganese. The manganese in MnO4, remember it's MnO4 minus. So oxygen is -8. And what plus -8 equals -1? It's got to be +7. So the manganese in permanganate, MnO4, is a +7. And it's going all the way down to a +2. That's the reduction. That's the species that is accepting the electron. And the process of accepting the electron, permanganate, now becomes manganese +2. That's your reduction. So this would be the oxidation reaction. This would be the reduction reaction. This would be the net reaction. And you guys know how to do this because you know how to balance redox equation. And so you can write the line notation. The line notation for this, again, iodine can't be an electrode. Why? Because iodine, even though it's a solid, is not tough enough to withstand electron transfer. So you need a sacrificial inert electrode. It could be a carbon graphite. You can do that, or platinum electrode, followed by a line. And then we have I2, solid. Okay, another line, I minus, because, oops, mistake. Okay, I2, 0 going to I minus is a reduction. It's not an oxidation. So right away you catch yourself. At least that's what you should do. So I'm going to change this. And I'm going to put in here I minus, aqueous, and I could put in here 1 molar because we're under standard state. And then it's I2. Okay, solid, because I2 is a solid. Double line, that's your liquid junction. That's where it's separated between the oxidation and reduction. And then in the second part, we have permanganate, MnO4 minus, aqueous, 1 molar, line, manganese +2, line, aqueous, 1 molar, and then say a platinum electrode or carbon graphite electrode, and that would be the line notation. So you can see that doing the line notation, if you understand what's going on, you can also get the line notation from that half reaction. Okay, at least know what species is converting to what from the net reaction. But the line notation is much easier to diagram out rather than drawing that picture right there. So here are the answers. Here are the answers for that. Oops. We already said that. Here is, in this particular case, I minus going to I2. There should be a line right there. I forgot to put that line right there because that's a phase change. MnO4, there should be another line right there. Okay. Going to Mn +2. And then what we have is copper solid. So that would be the line notation. And then this other one is classic. It's a metal converting its oxidation state. So the oxidation reaction is the copper. The reduction reaction is the zinc ion. And the metal itself serves as the electrode. So look over these, know how to take a line notation. If you are in lab, look at the electrochemical activity, because there's a bunch of examples like that. Okay, a bunch of examples like that. Here are more examples. Here we have zinc going to zinc +2, so that's the oxidation. We would write that right there. Nickel +2 going to nickel 0, you would write that right there. And then the metals, because nickel is a transition metal, zinc is a transition metal, they can serve as the electrode. Okay, you just have to know this. Iodine, yeah, it's a solid at standard state, but it's not a metal, it's a non-metal. So you can't use that as an electrode. You can't. Here's another one, thallium +3 going to thallium plus, chromium +2 going to chromium +3. Now, take a look at that reaction, because ions can't serve as an electrode. Okay, ions can't serve as electrodes. They're not metallic. Yeah, the element's metallic, but you can't have, there's no such thing as a metal thallium 3. Okay, it's got to be connected with some other, like an thallium oxide, yeah, you can have a solid of that. But what you need really in this particular case is an inert electrode to facilitate the electron transfer. So what you're going to do is put a platinum on both sides or a carbon. The oxidation reaction is the chromium. Okay, aqueous 1 molar. Chromium +3, aqueous 1 molar, double line, put a line right there, and then thallium +3, aqueous 1 molar, thallium plus aqueous 1 molar, and then platinum solid. That would be the line notation. You would need inert electrodes to make sure that the electrons can be shuttled. And so that's basically what we have here. I didn't use platinum, I used carbon. It doesn't really matter what inert electrode you use, as long as it's an inert electrode. What are the typical inert electrodes? There's 3 that you can use: carbon solid, carbon graphite, platinum, or palladium. Okay, those are the 3 that are generally used in electrochemistry: platinum, palladium, or carbon are typical inert electrode. Eventually, if you have enough electrons, these things can get oxidized. Okay, metals are oxidized, remember, but you need a very high potential. And if there's some other chemical that is easier to oxidize or reduce, then the chemical itself, the platinum or the inert electrodes, is not going to undergo oxidation reduction because it's always going to take a path of least resistance. If you can take that electron and shuttle it to a species that can use it at a lower potential, then it's going to shuttle that electron. Okay, but if it's a species that can't transfer that electron to a species with a lower potential, then eventually that inert electrode might get oxidized. Okay, if you have enough voltage in there to do that. And you can see right here, yeah, I'll show you that. You will find the potential for a platinum and, well, not so much carbon, that's not typical, but in here, here's palladium right here. Okay, here's palladium. You should also be finding something for platinum. Don't use this because this is not platinum going to platinum +2. It's platinum chloride. That's different. That's different. Here it is, the platinum electrode. That's 1.2 volts. So if there's another species that's connected to these electrons that will be more spontaneous, then these electrodes will not undergo redox chemistry. They're just going to transfer that electron. Okay, that's why we like to use these material, because they are so difficult for them to get oxidized or reduced. We're changing subject now. Okay, and why does one species want to give up electron while another species want to gain electron? Okay, what is the reason behind that? Okay, the question is, you have zinc solid and you have copper +2. Okay, why would zinc want to give up its electron to copper? Okay, what is the reason behind that? Okay, and you might take a step back and think about some of the fundamentals you guys already know. Okay, some of the fundamentals you guys already know is that when ionic substance form, sodium, so I'm taking a step back to some of the fundamentals that you guys know for you guys to understand why redox reaction occurs. If you look at an ionic equation, sodium plus chlorine, and you combine them under the correct conditions, okay, sodium metal, chlorine gas, then you get sodium chloride solid. Why does sodium chloride form? Why does that reaction go? You guys know it's because sodium has 1 valence electron So if it can give up its 1 valence electron, it'll have the same number of electrons as a noble gas. It'll have an octet. Chlorine has 7 valence electron. By picking up 1 more electron, then it'll have the same number of electrons as the noble gas. But there's 2 chlorine, so of course there's 2 electrons have to be available for 2 of the chlorines to have the same electrons as the noble gas, called the octet rule. Okay, so that's why you need 2 sodiums. So the reason why reactions occur in general is because the atoms want to be more stable and have the same number of electrons as a noble gas. When it has a complete full valence shell, then they're stable and they're totally satisfied. That's the driving force for ionic reactions generally. It's the same thing with electron transfer. It's not the octet rule, but zinc has a greater tendency to lose its electron and become zinc plus 2. Has a greater tendency to lose its electrons. Now, copper, in the presence of zinc, want to gain those electrons and go from copper plus 2 to copper 0. Again, depends on what reactions you're coupling. If you don't have zinc, if you have, for example, let's look at this table, and we have copper being coupled with iodine right here, then the copper is not going to get reduced. The copper is not going to get reduced, okay, because the iodine doesn't want to do that. That's why we have this electrochemical potential. It gives you the relative strength for the reduction process relative to hydrogen. Some has a stronger ability to get rid of its electron than others relative to hydrogen. So what you need to do is, when you couple these reactions and you want to see which works, you always got to make sure that one's an oxidation, one's a reduction, and yet when you add the potential, the E1 half, these are considered E1 half because it's half the reaction. When you add the E1 half, it becomes a net positive, because that would be the spontaneous reaction. So in this particular case, it would not work. What would happen is that the copper itself would not get reduced. The copper will get oxidized, because when it's coupled with the iodine, then the iodine will get reduced. And here's what I mean. If we take I2 going to I minus, and again, I'm not going to balance the equation, and we have copper plus 2 going to copper 0, and we know that this E0 for this is the way it's written. Both of these are reduction, is positive 0.5355, and this is positive 0.337. But remember, even though when you take 0.5355 and you added 0.337, you get a net positive, it's not physically possible. Why? Because both of these reactions are reduction. You cannot couple a reduction reaction with another reduction reaction. You can't have 2 reactions giving up electrons, okay? It's not going to happen. You got to have one giving up electron, the other one accepting. So if we make this, if we keep this as the reduction and we make this the oxidation, then that's a negative 0.5355. A negative 0.5355 plus 0.337 gives you a negative number. Not going to happen, okay? We need to figure it out so that one's an oxidation, one's a reduction. And when you add the 2 half redox potential, you get a net positive. Or at least a more positive negative value. A more positive negative value means that that's the reaction that is most likely to occur if you want to push that reaction with an external energy. Okay, the most positive potential is going to be the one that is most, again, the path of least resistance. So we're not going to make this a oxidation. That's not the oxidation. That would be the reduction, and this would be the oxidation reaction. And when we do that, okay, when we do that, let me clear this. Oops, sorry about that. Too bad there's no reverse sign. So it's the I2 going to I minus, okay, and then it's the copper plus 2 going to copper 0. That E0 value under standard state conditions was 0.5355. Sorry, I'm not showing you my screen. Okay. And then the copper is going to be 0.34, and they're both positive. So you can't make that the oxidation, because if you make that the oxidation, then you would get minus 0.5355. And when you add 0.5355 to 0.34, that would be a net negative. That's not the possible reaction. What you need to do now is you need to take a look at this right here. You need to make this reaction the oxidation, and you can still keep that as the reduction. So that would be positive 0.5355, because that's the way it's found in the table right here. Iodine, 0.5355. But now if we make the copper the oxidation speed reaction, we have to change that sign and make that a negative 0.337. 0.337 is what the book has. And now if we add that, you will see that the net sum is going to be positive 0.1985 volts. Okay. And a positive means it's a spontaneous process. So that's why we have these standard reduction potential table, because we can figure out which reactions will couple to what, which one has a stronger ability to give up electrons, and which one has a stronger ability to gain electrons when they both agree with each other. And so that the net potential is positive. That's the reaction that will occur. That's the reaction will occur. So make sure you understand how to use this table, in other words. Okay, so that's the driving force for these cells right here. That's the driving force for these cells right here. Let me clear this real quick. I gave you the analogy of water flowing. You need, in order for water to go through a pipe, you need some pressure gradient, and the pressure is going to drive that water to go through the pipe. Now, the bigger the pipe, the more water is going to flow. The greater the amperes, what measures electrons, the greater the number of electrons that's going to go to flow. The pressure gradient here is like the voltage, okay? The other way to think about it, it's like an object hanging off a ledge. When it's sitting there, it has a certain amount of potential energy. That's what we mean by the reactions. These half reactions, they have a certain amount of potential energy that's available for that electron to transfer, but it won't transfer unless it's coupled. It's like taking this boulder and then giving it a little shove so that now you can convert that potential energy to kinetic energy as it drops. The half reactions will not occur unless it's coupled. That's the little shove that will happen. And then when you couple it, then the electron will transfer depending on which one is going to be more willing to give up the electron, which one is more willing to accept the electrons. Okay. Now, electrons themselves are when we have these voltage, when we measure these voltage, it's what we call a it's an independent. Okay, it's an intensive function. You guys remember that? Intensive and extensive property. Okay, like density is an intensive property. Volume is not an intensive property, it's an extensive property. This goes back to your days of Chem 200. Intensive properties are properties that is independent of size. Doesn't matter how much you have, the density of water at 25 degrees is always going to be 1 gram per cc. Whether you have a thimble of water or a gallon of water, it's still 1. But the volume changes. Okay, a thimble of water is going to be small, probably 0.5 milliliters. A gallon of water is going to be huge, close to a liter. Okay, so the volume property is an extensive. The density property is an intensive, independent of size. Think of it this way: intensive, IN, independent, IN. Okay, so you guys should be able to correlate intensive and independent of size. voltage is independent of size. It doesn't matter how many, like your battery, okay? Whether you have a AAA or a AA or a size D, those potential are still 1.5 volts. The bigger the battery, the longer it'll last because it has more material to give you electrons. But the voltage is still the same. Doesn't matter how much, how big your batteries are, the potentials are still the same. So that means that the potential for these electron transfer to occur is independent of how much material you have. It depends on that. That'll only give you an idea of how long electrons are going to be supplied. In order to change the voltage, you need to change the material. You need to change the chemistry, okay? And that's why finding a magic battery, a solid state battery, is it's so important these days, because what you want to do is you want to find a battery that is going to be lightweight and gives you a lot of electrons for the duration that you have, okay? And what you will see in the standard reduction potential table is that, here, let me show you this. Which material gives you the most positive and most negative? Why most negative? Because when you switch the negative, it becomes a positive. Which material gives you the most positive and the most negative potential? It happens to be fluorine at 2.87. So the oxidation or the reduction of fluorine is 2.87 volts. And it happens to be lithium. Why do you think lithium batteries are so popular? For that material, when it gets oxidized, because remember, the reduction is negative, but if we oxidize the lithium, it'll be positive 3 point. So that's why we have lithium batteries all the time, because in terms of our standard reduction potential, it gives us the most bang for our buck. Okay, now if we can get a battery that uses lithium and fluorine, then we have a material that will give us close to 6 volts just for one cell. Okay, the problem, of course, is that lithium could be explosive. And so that's why they're trying to make polymers of that or different materials. And then fluorine is not a solid, it's aqueous. But these days, a lot of research, I just read this the other day, is trying to use, I think Toyota's battery. They're trying to make a battery that's better than Elon Musk, and they're using the fluoride. They're using this part of the standard reduction potential to make solid state batteries. Okay, so again, that's the insight that you guys have in terms of the research that's going on to make bigger, better, more efficient batteries that won't blow up in our faces. Okay, and that's important because our solar panels these days are really efficient, but it only works during the day. If we can store that energy that we are converting from the sun into the batteries, then that would be great. But the batteries are very expensive these days. Okay, they're very expensive, and we need something that lasts longer. Anyway, here I am again going off to a tangent. Let's go back over here, and then I'll finish this off. Okay, so in order for electrons to transfer, there's got to be a driving force, and that driving force are the half reaction. The half reaction, as you see in the standard reduction potential table. And you can see that it's like pushing a boulder off a cliff. The electron itself, it's going to originate at the anode, and it's going to end up at the cathode. So you can think of this illustration right here as the electron here that's being pushed over, and then that electron, as it falls, as it goes through a wire, can do work. Potential energy in this diagram, if it's a motor, is going to get converted to kinetic energy. Okay, and when that happens, then you can do work. When you take electrons and shuttle it in a wire, then you can do work. The idea here is that the bigger this gap, the more work you can do. How do you change that gap? You can't change the size of the electron. Even if you got 40 here versus 4, that gap is still the same. It just means that you can sustain that energy longer with 40 electrons versus 4. Again, that's the size. It doesn't change the potential. What you need to do is you need a different reaction that have a bigger difference between the oxidation and reduction. Then you can get more voltage, more energy to do more work. Okay. So here it is right here. This is the scale. Again, lithium is 0.304. We couple it to fluorine. So we make this an oxidation lithium going to lithium plus. So now that's not negative 0.304, it's positive 0.304, 3.04, I mean, and we couple it with the reduction of fluorine. So we have a reduction in oxidation. We get a potential in there of about 5.91 volts, close to 6. That would be a perfect battery, except paper process, paper thinking is different from reality. Okay, in paper, it looks great. That's what we want. Reality, how do you get a gas into a medium? Okay, the gas will evaporate. So we need to figure out a different material. That's why research is so into place. So like I said, electromotive force, that's E0. It's also called the electromotive force, is the size, that size right there depends on this size right here, depends on the species that you're talking about, the oxidation reduction. But again, it's independent of size. Doesn't matter how many moles you have based on your reaction. It depends on the species that you have to give you different potential. Like I said, it's an intensive property. Okay, it's an intensive property. So in a stoichiometry reaction, this is the stoichiometry reaction. Let's say we have lithium, and the lithium gives us a potential minus 0.3045 volts. That's the reduction potential. If we multiply that by 2, we change the stoichiometry now to 2 moles of lithium. Yeah, the potential is going to be multiplied by 2. But you got to remember that this voltage is the coulomb per electrons. Voltage is defined as coulomb per electrons. So when we double the coulombs, we also double the electrons. So it's like 6.90 divided by 2, which is just 3.045. Because what we've done now is we've doubled the number of electrons. We got to divide by 2 rather than 1. That's why it's an intensive property. Okay. When we change the number of moles, we change the number of moles for the chemical, but we also change the number of moles for the electron. And the voltage is a coulomb per electron. So yeah, the coulombs double, but the electrons also double. And so when we divide it, we get the same number. That's why it's an intensive property. Okay, it's an intensive property. That's what I wanted to illustrate here. So this is a standard reduction potential, and this one right here, this particular table, again, here it is. It's a shortened version of what I've been showing you. Okay, the top is going to have the most positive value. The most positive value in this standard reduction potential table is going to be the reaction that is most likely to undergo reduction, gain electrons. The bottom, because it has the most negative value, are the chemicals that are most likely to undergo oxidation, because the negative of that, the negative process is an oxidation reaction. And when we change a reduction reaction to an oxidation reaction, we change the sign of the potential. And that's what we see right here.